Hi! In this video, we'll show how to use traffic class counters to troubleshoot data center networks. Here's our agenda. First, we'll explain a bit about how packet classification works. Second, we'll find our way through traffic class maps. We'll evaluate different types of queues, how to take advantage of queue counters for troubleshooting purposes, how to copy a DSCP value from encapsulated packets to outer headers. We will explore our lab topology. We will influence path decisions in an ECMP network. We will demonstrate how to find a packet loss in a VXLAN and ECMP topology. When an IP packet transits through a network device, the content of its headers is passed. Based on the value of the differentiated service code point field, or .1q class of service, the packet is assigned to a traffic class or another. Let's have a look at how a DSCP value is mapped to traffic classes on an Arista device. We will use the well-known value 46 as an example. Number 4 in the tens position has to be mapped to D1 in the column of DSCP to traffic class map. Number 6 in the unit position has to be mapped to D2 in the row. Let's find the corresponding values 4 and 6, respectively, in the column and the row of that table. Now that we have found the values that we are looking for, let's find the crosspoint, as we would do with coordinates in a battleship game. Number 5, hit and sunk. This is the traffic class that would be used to send packets with DSCP 46. It is important to notice that the default traffic, having DSCP values from 0 to 7, is assigned to traffic class 1, while DSCP values from 8 to 15 are assigned to traffic class 0. This inversion downgrades unimportant traffic that was previously marked with a selected value to the lowest queue, while leaving untouched the low priority but still relevant majority of packets with DSCP 0. There are different approaches to how queues have to be emptied. The round-robin scheduler goes through all the queues, takes a single packet from each one of them, and forwards it like it is happening in our simplified model with 3 queues only. A red packet is taken from queue 3, a yellow packet from queue 2, a green packet from queue 1, and then back to queue 3 again. In this way, an equal amount of bandwidth is allocated to each queue. That prevents queue starvation, a condition where low-priority queues are never served when higher priority queues keep the scheduler busy. However, in a real-world scenario, there are different bandwidth and latency requirements for each type of traffic. For instance, control plane and voice traffic don't occupy a lot of bandwidth, but have to be sent immediately. Data plane traffic is usually more tolerant of delay, but tends to monopolize all the bandwidth available. Storage and multicast require high bandwidth and relatively low latency at the same time. Complex policies can be created with weighted round robin, which means that more bandwidth can be guaranteed to a traffic class while accepting that fewer resources are left for the others. Those policies are typical of oversubscribed networks and imply a contention for bandwidth. However, data center network design avoids competition between traffic flows by reducing link oversubscription to a minimum. The default scheduler in Arista devices is based on strict priority. No packets from lower queues are sent before all the upper queues are empty. In our simplified 3-queue model, we can see that no packet from the yellow queue number 2 will be forwarded until there are still packets in the red queue. Similarly, no green packet from queue 1 will be touched until no packets are left in the yellow queue. We will try to send an ICMP echo request packet with a non-zero TOS value from a client and see which traffic class we are going to hit on a transit switch. We selected value 184 because it corresponds to null explicit congestion flags, which are the rightmost bits in TOS and the encoding of DSCP 46 in the leftmost bits. A quick way to obtain the TOS corresponding to a specific DSCP consists of multiplying that value by 4. In Show Interface Counter Queue output, we can see an increment of 1 packet in traffic class 5 of interface Ethernet 10/1 and 17/1, which are the transit interfaces for our test packets. This method works fine with regular packets, but many data center networks are based on VXLAN or other packet encapsulation techniques, where inner packet headers cannot be passed. Some Arista platforms can copy DSCP values from encapsulated packets to outer packet headers. Our flagship R3 series has this feature enabled by default. The details can be found in the DSCP and ECN rewrite for VXLAN bridged packets, TOI. Our trusted 7050X3 leaf switches can do that with a single liner configuration. More information on the VXLAN DSCP mapping document. We can enable this feature under VXLAN interface configuration with the command VXLAN QoS DSCP propagation encapsulation. With both platforms, Show VXLAN QoS command can be used to confirm whether DSCP propagation to the outer header is enabled or not. Now, let's put our lab topology under the lens. Host 1 is a client connected through a port channel to leaf switches. Leaf 1 and leaf 2 pair form a VXLAN VTEP. Spine 1 and spine 2 are our spine switches, and the other VTEP is composed of leaf 3 and leaf 4. Host 2 is a logical cluster composed of 2 physical hosts connected with a multi-chassis port channel. Multiple paths with the same capacity and routing cost are available at the same time. Packets can be sent through all available links, permitting redundancy and increasing the total throughput. On a less bright side, ECMP networks are difficult to troubleshoot, as we cannot predict which path our packets take. For instance, users of our lab topology are complaining about traffic losses, while all of our ping tests are successful. We need to find a way to probe different paths and identify the lossy link. Packet allocation happens per flow, which means all packets with the same set of Layer 2, Layer 3, and Layer 4 headers are assigned to the same link due to a hash calculation. Now, a few questions. Can we control ECMP path selection with purposely crafted packets? Which fields do we need to change to make that happen? Source and destination MAC and IP cannot be touched without compromising reachability. ICMP packets are Layer 3, hence do not have a concept of port. We need some tool to generate L4 traffic and modify source and destination ports. Traceroute is readily available in most operative systems. It can generate UDP traffic and includes options to specify not only source and destination ports, but also TOS values. When using traceroute on networks running Arista devices, it is recommended to use a destination port that is allowed by the control plane policy, otherwise UDP test packets will be silently dropped without generating the ICMP messages port unreachable or time to live exceeded that we expect as a response. The traceroute command we are going to use sends 5 packets with a time to live of 6 hops, a minimal probe interval, and timeout to speed up things a bit. But most importantly, it includes the indication of a source UDP port that we are going to increment at every test. A successful test on a healthy path would report a line with the destination address and 5 different round-trip timers. A faulty path would generate an entry with 2 asterisks that replace one of the RTT values. From the test host one, we keep on repeating the same traceroute command by incrementing the source port by 1 unit. We already tried source ports 51,000 and 51,002 with no issues. Next one is port 51,003, then 51,004, 51,005. Oh, we got it! 51,005 is the source port that makes the ECMP path selection algorithm hit the faulty path. To identify that path, first, we need to clear interface counters on all transit switches, and then start the watch diff show interface counter queue detail pipe grep double quotes UC5 /pipe TC5 double quotes pipe enzine command. Let's take a quick peek at the test host and repeat the same traceroute command. Now back to the switches. We can see that all 5 packets hit leaf 1 on traffic class 5 of the interface Ethernet 55/1. That is connected to the spine 2. The egress interface Ethernet 9/1 got only 2 packets. We will now inspect spine 2. In short, we configured a policy map on the ingress interface Ethernet 17/1 to simulate a lossy link. In summary, our troubleshooting steps are: Number 1, clear the interface counters on all switches. Number 2, run the traceroute command by incrementing the source port number. Steps 1 and 2 have to be repeated until we hit the lossy path. Number 3, check the interface queue counters of all switches. Number 4, investigate the packet loss reasons on the first device in the path, showing fewer packets than the number of packets that we sent. That's it for today. I hope you enjoyed this video and see you next time.